Here is your text combined into a single paragraph without omitting any words. In 1823, German astronomer Heinrich Olbers looked up at the night sky and saw darkness. Einstein's paradox. He wondered, if the universe were infinite and eternally static, surely the night sky should shine with the light of infinite stars, a dazzling brilliant sky. Olbers' paradox was so compelling that many considered it proof of a finite universe, a cosmos that at some point simply ends. It wasn't until a century later, when Edwin Hubble observationally established the reality of an expanding universe, that Olbers' paradox was firmly solved. Olbers' second assumption was wrong. The universe is not static. But what does modern astronomy have to say about the size of the universe, though? Is it finite, and if so, does that mean there's an edge? Or could be infinite? An endless ocean of space, with challenging philosophical consequences if so. The big question: how big is the universe? It's the sort of question that a child often asks when they first encounter the concept of space, and yet it is one which continues to perplex and haunt astronomers. It's often said that studying the cosmos is a humbling experience, for whilst early thinking considered the Earth, Sun, and Moon to be the de facto universe, our modern understanding establishes one that it is unimaginably larger. At each stage in science's journey of revelation, humanity has had to swallow another great demotion, quietly ushered down to an ever lower seat in the great cosmic hierarchy. These demotions began within the 16th century with Copernicus and Kepler, challenging the geocentric view of their time and revealing that Earth is just another planet. Next, in 1838, Friedrich Bessel pioneered the parallax method to measure the distance to the star 61 Cygni, a staggering distance of more than 10 light-years, or approximately 100 trillion kilometers. In 1920, famed astronomers Harlow Shapley and Heber Curtis debated at the Smithsonian Museum of Natural History as to whether distant nebulae were small clouds on the outset of our galaxy or entirely separate galaxies far further away. Soon after, Edwin Hubble established that Curtis was right by proving that Andromeda was in fact far outside of the Milky Way galaxy, at a distance of 2.5 million light-years. Equipped with far superior telescopes, modern astronomy has pushed our observations to distances unimaginable even to these pioneering astronomers. For example, look at this image. It is one of the most incredible photos ever taken. You are looking at the most distant galaxy ever observed, GNZ 11. This galaxy is so far away that the light forming this image left it 13.4 billion years ago. A photographic time machine. The universe itself was just a few 100 million years old at this time, and so GNZ 11 is a glimpse at what the first galaxies to ever form looked like. If we could see GNZ 11 as it is now, it would probably be unrecognizable, and in fact likely have merged with other galaxies along the way. The problem: GNZ 11 is estimated to be 32 billion light-years away from Earth. At first, this seems impossible. If the light left 13.4 billion years ago, surely it's 13.4 billion light-years away. But that again falls into Olbers' fallacy. The universe is not static. In fact, GNZ 11 has been hurtling away from us ever since the light from this image left. Or more accurately, I should say, space has been expanding, and so a correct calculation of its current distance needs to account for that fact. Objects like GNZ 11 can thus be thought of as establishing a minimum size of the universe. But given that it's 13.4 billion years old, and the universe is 13.8 billion years old, then surely it should be possible to image an object that's even older and thus further away, and that would extend this minimum size yet more. It's at this point it's useful to talk about two distinct concepts: the visible universe and the observable universe. Neither of these really have anything to do with telescope capabilities, but rather true limits dictated by space-time. The observable universe will be the distance to an object that was present at the very dawn of the universe itself and whose light was now just reaching us. Of course, the universe didn't have any stars or galaxies at the very beginning, so there are no objects to detect. Nevertheless, based on the expansion rate of the universe, as measured using telescopes like ESA Planck mission, we estimate that this distance would be 45 billion light-years away. If something was further away than this, there simply wouldn't have been enough time yet in the universe for its light to reach us. We often say such objects lie beyond our horizon, like a ship that has dipped below the ocean's horizon. There's simply no way to see them whether they exist or not. In fact, the horizon of the observable universe has a special name: the particle horizon. The particle horizon. The visible universe is actually subtly different from this. For the first few 100,000 years after the Big Bang, the universe was so hot it was an ionized plasma which essentially acted like a thick fog. Light couldn't traverse the universe without interacting with one of these ions. It's only when the universe cooled enough atoms to form, clearing. Here's your provided text restructured into a single paragraph without omitting any words. The fog away in an epoch known as reionization, that light can freely travel. So the visible universe is a little bit smaller than the observable one, by about 1 billion light years. This is a truly mind-bogglingly big number. No words or analogies really do justice to just how preposterously large the universe is. But it could be even bigger? Take the observable universe, corresponding to a distance 45 billion light years away. Usually, at this point, videos like this take that number and double it and call the diameter of the observable universe. We have to be a little careful about that because what if we see another GNZ11 over in the opposite direction? Not a galaxy similar to GNZ11, but the actual GNZ11. For example, if the universe has a positive curvature like a sphere, then it's quite possible we would see the same galaxies and patterns in different directions. If that were true, doubling this distance wouldn't correspond to the diameter, but something more like the circumference of the universe. These repeating patterns seem to offer a possible way, then, for the universe to be smaller than we might naively have guessed. To answer this, let's return to that moment of reionization in the early universe. This is the oldest light we can observe, and it comes from all directions. After all, the entire universe was filled with this ionized plasma. The light is known as a cosmic microwave background, or CMB, and it encodes the temperature of the universe at this time. Any patch of the CMB more than 2 degrees away from another patch is too far away to have had time for light to travel between them, at least given the age of the universe at the time, just 380,000 years. So, if we see a particular pattern or ripple repeated in the CMB but separated by several degrees or more, that could reveal the universe wraps around itself, implying a smaller universe. Detailed studies of the CMB reveal no such repeating structures, though. The lack of such structure can be used to put lower limits on the size of the universe, but not surprisingly these limits essentially correspond to the approximate size of the observable universe. So the full universe really does appear to be at least as large as the observable part. Now let's suppose someone lives in the galaxy GNZ11. They would be able to look back along that line of sight and see the proto-Milky Way as a faint distant galaxy too. But what if they looked in the opposite direction? Would they see an edge or some kind of physical boundary? Whilst we cannot truly know what they might see, a basic assumption in astronomy is the so-called cosmological principle, which states that we do not live in a special part of the universe. So what we see is typical, and by extension what GNZ11 inhabitants see is likely not much different from us, at least on the largest of scales. The cosmological principle does not rigorously prove anything about the size of the universe, but rather forms a logical argument. By it, inhabitants at the edge of the observable universe should themselves be able to see another entire observable universe around them. Filling out across the edges, this would give us a volume 180 billion light years across. We have to tread carefully here, though, because the size of the universe could still be smaller than this if it somehow wraps around itself. Consider in this direction at the edge of our observable universe we have Alice. Alice looks out in that same direction and can see at the very edge of her observable universe someone else. Let's call him Carlos. Now let's go back to Earth and look in the opposite direction. Over at the particle horizon here we see Bob. As before, Bob looks out in the same direction and sees someone else, just like Alice did. However, Bob is in fact looking at Carlos again. To each individual observer, there is no repetition, but Alice and Bob are in fact both able to see the same person, Carlos. And since Alice and Bob live far beyond each other's particle horizons, there's no way they can communicate this to each other. No one is able to tell that the universe repeats and thus are left none the wiser. So we can't really use a cosmological principle to argue for a much larger size to the universe. All we can say is that we don't see repetition within our horizon, and thus the universe must be at least 2 by 45 billion light years in extent, or 90 billion light years. Repeating patterns are not the only way to place limits on size, though. Already I've mentioned the concept of curvature, and here perhaps we might finally have a clue unto its true size. Standing on the Earth, we can't directly see its curvature because the radius of curvature is just so vast. But the curvature can be detected with some geometry, as was famously done so by Eratosthenes of Cyrene 2 millennia ago by comparing the lengths of shadows of sticks in the midday sun at two different locations. In an analogous way, astronomers can use the CMB radiation and some geometry to measure the curvature of the universe itself. A simple way to think about this, on a positively curved surface, like a sphere, two parallel lines will eventually meet. For example, if we both head straight north, no matter where you live, I will eventually bump into you at the North Pole. On a flat surface, the lines stay true and parallel forever, but on a negatively curved surface, like a saddle, they diverge. So how curved is the universe? The curvature parameter, known as omega_k, has been refined ever more over the years thanks to missions studying the CMB. The earliest estimate, done by the Boomerang experiment in 2000, found it to be flat to within 6%. 18 years later, ESA's Planck mission published our current most precise estimate to date, which is again flat to within 0.19%. It is truly an amazing technical feat by legions of astronomers involved that we can measure the curvature of space at this level. But what does this really mean? Let's consider. Let me know if you like this cleaned up for clarity or formatted differently. Here is your full text converted into a single coherent paragraph with no words omitted. That the number is indeed exactly zero, a flat universe. It's at this point that many often look at that flatness and interpret it to mean the universe must be infinite. Look, it's perfectly reasonable to suggest the universe is infinite as a possible hypothesis, but it's not true it's the only explanation. It's a non sequitur that flatness requires infinite space. To cosmologists, flatness doesn't really mean what we might naively think, and a flat universe can be finite. In fact, we've already discussed an example of such a universe. Let's go back to our friends Alice, Bob, and Carlos and imagine the universe really is two-dimensional, like a sheet of paper depicted here. If we had a warp drive, we could fly from Earth in the direction of Alice, and when we cross Carlos, we would re-emerge on the other side and be heading home again. This is probably familiar to any computer gamers. Games like Pac-Man and Asteroids would often feature this rule. Since the left side and right side really correspond to the same line, the universe wraps around itself here. If up and down go on forever, then what we essentially have is an infinite cylinder. In fact, since I made the cylinder from a two-dimensional sheet, it's really a two-cylinder. The two-cylinder is really defined by left goes to right Pac-Man rule operating on the original 2D sheet, what is known as a fundamental domain. That's what makes it a two-cylinder. When we roll it up in 3 dimensions, we're embedding the two-cylinder into 3-dimensional space, but that's just us embedding it into 3D. So even though it looks curved when embedded in 3D, that's just a product of the embedding, it's actually still a flat geometry in its fundamental domain. Now this two-cylinder doesn't really save us from an infinite universe because its length extends out to infinity. So let's go back to our fundamental domain and look at our rules one more time. What if we add another rule that going past the upper edge takes you back to the lower edge? Now we truly have full Pac-Man rules. A fundamental domain described by these two rules is no longer an infinite two-cylinder, but a finite two-torus. We call it a torus because if you imagine re-rolling it back up, we first get the cylinder as before, and then we have to connect these two ends together. In practice, if I try to do this, I'd have to stretch out the material, distorting the plane, but we can see that it should form something like a donut-shaped torus. Now, at this point, it's useful to discuss John Nash, who you probably know from the biopic A Beautiful Mind. The fact you have to stretch and distort the original plane to create the torus shape means that you failed to isometrically embed it. And that isometric part is key because without it, distances are distorted in a way we don't see in the universe around us. But John Nash proved that it was in fact possible to isometrically embed a two-torus into 3 dimensions by adding waves and waves of tiny corrugations during the embedding procedure. This was a beautiful proof, but it didn't actually reveal what this two-torus embedded into 3D would actually look like. In 2012, a French team used supercomputers to finally calculate what the shape looked like. This stunning morphology is in fact flat in the fundamental domain, and adheres to the two-torus Pac-Man style rules. The French team went a step further and even uploaded a 3D print design up on their website. Thanks to those corrugations, it's a formidable 3D print to actually pull off though. I asked around several New York printing agencies about this, and they all basically just said straight up no. If there was anyone that could pull this off, it was going to be Joel, also known as a 3D printing nerd, an awesome YouTube channel that explores everything 3D print related. He took this on and has even created an awesome video describing this feat. Please do check it out when you're done here. So here it is, a 3D embedded 2 torus. It's even more beautiful to hold and touch than the renderings. And what's truly mind-blowing is that I may actually be holding the universe in my hands, a finite flat cosmos embedded in some higher dimensional space. Of course, remember that this is a 2 torus. It's made from a 2-dimensional plane. Since our universe has 3 spatial dimensions, the universe would need to be a 3 torus, so a kind of hyperdimensional extension of this incredible shape. The 3 torus is in fact just one of 10 different possible manifolds that could represent a flat, finite universe. 6 of these are called orientable and include the 3 torus. But for our so-called non-orientable manifolds, and include this thing, the bizarre Klein bottle, a mind-bending shape of technically zero embedded volume. This orientability property is best understood by looking at a simpler manifold, the Mobius strip. If you travel along the Mobius, after one circuit your left and right have switched over, you become a mirror version of yourself. If the universe is truly one of these non-orientable manifolds, it would have some bizarre consequences for a hypothetical warp ship. Leave Earth and travel in one direction long enough and you return home. Arriving back on Earth, you would at first feel the familiarity and relief of being back home, but would quickly realize something was off. Your family's faces were mirror versions of before, their watches ticked anti-clockwise. But from their perspective, it would be you who was changed, and taking you to the doctor for medical examination, they discover your heart was now on the right-hand side. All 10 of these manifolds are perfectly consistent with our observations, and all are finite. So any of these could be true, but there's another possibility. The universe could be truly infinite, either an infinite flat fundamental domain in all directions, or a negatively curved infinite saddle-shaped universe. Either way, we are forced to face an ontological crisis. What if the universe is infinite? Infinities are uncomfortable to physicists because they bring along some disturbing consequences. Given infinite possibilities, everything that can happen must happen an infinite number of times. In seeking a way out of this, one might consider that yes, perhaps space is indeed infinite.
Sunlight,
at some
racing
point
across
its
the
nature
vacuum of
radically
space,
changes.
takes about
There's
4
an
hours
end
and
to the
15 minutes
universe.
to reach
Indeed,
Neptune from the
there's some
Sun.
theoretical work that
This
might
staggering
at first seem
distance
fit the
close to
bill.
Earth since it
In the
dominates
so-called
our night
eternal
skies,
inflation
but in
model,
reality the
our
moon
local
isn't this
universe
close
is
to
a
our
bubble-like
planet,
region
it's
with a
actually about this
hyperexpansion
far
phase
away,
known as inflation to T. But travel far
384,400
enough,
Voyager
and
1
you'd
has
enter a
travelled
region
for
where the
over 4
inflationary field
decades,
has a different
covering a
state,
staggering
expanding
distance of more than
space so much that
22
each bubble
billion
universe
kilometers
is
from Earth.
separated by unimaginable
It's the
distances.
farthest human-made object
However,
from our planet.
since the entire landscape is
986
still
times
infinite,
further
there
away
would be
from
an
Earth than
infinite
the
number of these
astronauts who
bubble
landed on the moon
universes.
were. In
So,
addition, the
in
time
truth,
delay
this
for
doesn't
sending
really
a message
solve our
from
dilemma.
Mars back to Earth
So let's
isn't
just
Where the
stop
sun's
hiding
solar
and
wind
face
is
the
stopped by the
possibility head-on.
interstellar medium.
An infinite cosmos.
This is where the
Infinities
influence of our
disrupt
sun
probability theory,
ceases and
since
the
all
vast
events have a
realm of
probability
interstellar
occurring an
space
infinite
begins.
number of times, like infinite monkeys on infinite typewriters. It challenges a cosmological principle, because what does it really mean to assume you're typical if there's an infinite number of outcomes out there? At a human level, this infinite universe opens a door to some unsettling consequences, because it means that there's an infinite number of yous out there. Not just similar, but yous with the exact same arrangement of molecules and atoms, right down to the quantum states of your subatomic particles. That immediately provides a kind of way out of the no-cloning theorem, a quantum theory proved by James Pott that states that it's impossible to ever create an independent and identical copy of an arbitrary quantum state. If these clones share every single quantum state to you, surely that is you. And indeed these doppelgangers would sit inside an entire universe that was identical to our own right down to the last atom. Each one watching this video right now, each one their jaw dropping, their sense of self-dissolving as they challenge the very meaning of who they are. Yet more, in the past, in the future, there are infinite doppelgangers of you slightly offset in time, a version of you one day behind, 2 weeks ahead. You are everywhere, and you never end. Despite the existential crisis this carries, it perhaps provides some relief in other ways. For our close loved ones that we've lost continue to live somewhere, both offset in time, but also through different choices. An infinite number of loved doppelgangers who didn't get in the car that day, who decided not to take those terrible drugs, who got to hospital in time. Still out there, somewhere, just preposterously distant. At the same time, an infinite universe can also, paradoxically, feel empty and nihilistic. For many, we define our goals in life in terms of our impact on the world. But that impact dissolves away in infinity. For example, if your mission is to reduce suffering amongst humanity, it is challenged by the fact that in an infinite universe there is infinite suffering. And whatever you subtract from infinity, it's still infinity. And likewise, there is infinite happiness. So if your goal is to increase happiness, surely your actions are utterly futile. As we look further and further out, we perhaps finally turn back to inner space. We can't affect an infinite universe, or even realistically the infinitely smaller one we see around us. Rather than trying to derive meaning from our impact on the cosmic scale, the ensemble of space, meaning might actually be much closer to home. Because whilst there might be an infinite number of views, only you can control your actions today, how you choose to live your life, how you treat others, and so even the smallest act of kindness carry infinite weight. So until the next video, stay thoughtful and stay curious.